average of the minerals and the fluids. Here, instead of brine, say you could have a fluid composition. And if you do that, you need to take into account the saturations. And then convert that to gradients. Multiply times G. If it's field units, you don't have to multiply by G, remember. It's already there, the G. And if you wanted to talk in terms of fracture gradient, you will have to convert that to pounds per gallon. Yes, Ms. Kyle.
Would you give us the densities of all these different materials?
So, in the back of the exam, you will have the unit conversion. Here you have the gallons, and over here, here you have the pounds. You have everything.
Nothing in a conversion is like the density of like chloride or feldspar.
Oh yeah, I'm going to give you that. You don't have to know that by heart. So for example, in here, they are not written in here, but this was the exam before I solved it. If you look at the actual exam, you have a specific gravity of those. Okay? Let's see the next problem. It's a horizontal stress calculation using tectonic strains. So you first calculate total vertical stress, calculate pore pressure, calculate horizontal stress, in this case without tectonic strains, and in this case with tectonic strains. You add to that pore pressure, you get horizontal stresses. Yes?
So horizontal strains and tectonic strains are the same thing?
Yeah. Yeah, usually tectonic strains are horizontal. Any question about this problem? No? Okay, let's go to the following one. This is a problem of triaxial tests. Okay? You have the confining pressure or confining stress, the same thing. You have here the measurement at the load cell. So remember, this is going to give you the deviatoric stress. Notice that here you have force, okay? You don't have stress, you have force. To go from force to stress, you need to calculate the area of the sample. This is what you did in the lab too. So confining stress or confining pressure, same thing. Deviatoric stress, after that you can calculate effective radial stress, effective axial stress at failure. Failure or peak, that's the same thing, okay? Once you have this, you plot all of those in this sigma 3 versus sigma 1 plot. You draw a line with a ruler, and you find what is the intercept. You calculate what is the slope. So if I were to calculate the slope here, probably what I would say, okay, I like these 2 points because they are in the grid. So here, what is the difference from here to there is how much? 4,000, right? And the difference from here to there is 800. So 4,000 divided by 800, that's going to give you what is Q. And you are asked to draw the more circles too. So more circles, all you have to do is you have sigma 1 and sigma 3, and you just draw those ones here in the axis, and you throw the more circle in the middle. Try to make some effort, please, to draw some nice more circles, like not something like that, okay? Sometimes I see that in exams. That's not a circle. It's not even an ellipse. So try to draw nice more circles. Because if you don't draw a nice more circle, you may throw like a failure line over there, and that doesn't make sense, okay? So try to draw a nice more circle, and then draw a line that goes through that, and that's everything you have to do for that one. And I'm going to give you these equations, but remember, these two are related. These two is the same thing, exactly the same thing, just drawn in different spaces with different coordinates. And that's it for 2016. Any question about this one? No? Let's see what we have in 2017. Conceptual questions. Here you have a problem which is exactly the same as the one in the homework, okay? We have a bulk density that changes with depth. So you have to take an average of these. Multiply this time times the average of that. Should we go to the next one? Yes? Okay. This is a real application problem, okay? In this real application problem, you have vertical stress in this line, SV, pore pressure in this line, minimum horizontal stress and maximum horizontal stress calculated with tectonic strains. Equations very similar to the ones you have used. And from this real data, what I'm asking you is to interpret that, okay? If you're a fracture engineering, at some time probably there's going to be somebody that is going to give you these stress profiles, and you have to decide where to place the fracture. So you have to be able to read these type of plots. For example, here you see perforations are here, there, there, there. This is a vertical well. So if you now, I'm not asking you to compute vertical stress. You have vertical stress over here. I ask you to compute the depth, assuming a gradient, a reasonable gradient. You could assume a gradient in this case, if you're a little bit pickier, you could actually calculate that gradient from the data, because you have here depth and you have the variation, so you can calculate that gradient to estimate more or less depth. The second one is I'm not giving you the overpressure parameter. You have to calculate that one. And you can do that because you know what is pore pressure, which is this line. You know what is vertical stress, which is that other line. You can calculate the pore pressure. Notice this is a oil-bearing shale. Pore pressure is very high. And looking at stresses, you can say whether this is strike slip, reverse, normal, whatever case you have. And here, obviously, if these stresses are different, it's because already there is a tectonic strain. And even more in this case, the horizontal stress is higher than the vertical stress, so that means that there is actually a compressive tectonic strain. And the last one is very similar to the one before. And you have pore pressure, and you have to calculate sigma 1, sigma 3, plot all of those in a line, and do the same thing that was required in the other one. All right? So, guys, let me know if you have any questions. Make sure that you go again as you review your notes, that you also go through the lab test, okay? You have to be able, in the test, to process raw data in order to compute Young modulus, Poisson ratio, unconfined compressive strength, tensile strength. You have to know how to do that. I'm going to give you the data. So it's to the labs, to the laboratory reports.
Okay.
Right? Because you have to be able to compute Young modulus out of raw data, okay, and Poisson ratio too. All right, guys. I'll see you tomorrow.